Now we're going to look at an example where we're still going to use the logarithmic differentiation to tackle it, because this definitely looks far away from the exponential function e to the power of x, or like 10 to the power of x that we did in the last video. This now is 3 to the power of x squared. So logarithmic differentiation will allow us to tackle this again. So we're going to take the log of both sides, but not any log. We're going to take the log base e, which is ln. So we actually take the ln of both sides. In the other video, I made that line blue because we're not doing calculus, so I should make this one blue as well. The reason we take the ln or log of both sides is to allow us to use the rule of logarithms that says that exponent can come down. Now the exponent is not just a plain old x, it's an x squared. This does, however, gain me access to the variable and makes our differentiation a little easier. We'll take the derivative of both sides. The derivative of ln y is 1 over y, but we're differentiating with respect to x, so we need the dy by dx. This is similar to the question we had before. Remember that ln 3 is just a number. So you can imagine if this was 7x squared, then the derivative of that would be 7 times 2x, or 14x. But it's not a 7, it's a ln 3x squared. But it's still just a number, just like 7. So the derivative is, well, the coefficient just stays there, ln 3 times the derivative of x squared is 2x. Then we multiply those together. Now, ln 3, the 3 is not a number, it's a ln 3. It's not a 3. So it's 2 times ln 3 brings it out front. And then times x. Now, you might actually see it better if we just bring this whole thing out front and go 2 to the x, ln 3. So that is the derivative of ln 3 x squared. Just like the derivative of 7x squared, the 7 stays there, ln 3 stays there. Differentiate the x squared part and multiply as we can. So on the right-hand side of this, this becomes 2x ln 3. 2x ln 3. It's not a product rule because this is not a function, it's a number. All right, we now got to isolate for dy by dx. Since it's dividing by y, we're going to multiply by y. So y times 2x ln 3. And then replace the y with the original question. The y was 3x squared back in the original, times 2x ln 3. And we can't simplify that any further. This 3 is a base and an exponent, so I can't multiply it by the 2. The x and the x squared are not the same. I can't multiply those. One's an exponent, one's not. And so that's it. That is our answer. That's the derivative of 3 to the power of x squared. All right, one of the things you should have noticed is the reason we take the ln, or in this case the ln of both sides, the log or the ln, is because there are all these laws of logarithms and laws of lns that allow us to make our question easier. That is really valuable for a question as nasty as this one. So we can answer this 2 different ways. It is one that we could have done in our differentiation unit. We might have done something like this, where we use the quotient rule. And I'll actually show you the entire solution with the quotient rule. I'll show you that the quotient rule will work in these types afterwards. But I'm going to show you how logarithmic differentiation will allow us to use the laws of logarithms and lns to make this question much easier to differentiate. So I'm going to start by taking the ln of both sides. And while I'm doing it, notice that it's square root of 4x plus 5. So we already know a strategy for dealing with square roots. Change it to the exponent 1/2. So I'll do that at the same time as taking the ln. Now, one of the laws of logarithms we've seen before, bringing that exponent down. But the other law of logarithms, or lns, is if you're taking the ln of a quotient, you can take the ln of the top, subtract the ln of the bottom. So the ln of the top is x times 4x plus 5 to the 1/2 minus the ln of the bottom. So what this has allowed me to do is avoid using the quotient rule. But I can go even further. Now I'm taking the ln of a product. There's the first function, there's the second function. If I'm taking the ln of the product, I can take the ln of each parts of that product and add their answers together. Remember, this comes from the laws of logarithms. It says logarithms are exponents. Remember, when you multiply powers of the same base, you keep the base and add the exponents. Since these are exponents, we can change them into taking the ln of the first one plus the ln of the second one. And then minus, because we're dividing by the third one. Okay, so now I've taken this big division problem and I've spread it out into a bunch of smaller questions that are much easier to do. But I can go even further and use the law of logarithms for exponents. So this is ln x plus, since this is ln of something to a power of 1/2, that 1/2 can come out front, just like we had done in the other questions. So that makes it even easier. Similarly, this is ln of something to the power of 2. So that 2 can come out front, and I get that. So all I've done is changed the question. I haven't changed the actual question, I've changed the appearance of the question using laws to make it something that's much easier to differentiate. So now I think I'm ready to differentiate. I take the derivative of all these lns. I'll start with ln y, which we've done a number of times now, is 1 over y times dy by dx. But now I just have to look at these three parts as their own little question. So just looking at the ln x part, the derivative of ln x, 1 over x. Don't need the dx by dy or dx by dx because I'm differentiating with respect to x. Next, I have the ln of 4x plus 3. Well, the coefficient just stays out there. The ln of blah is 1 over blah, so it doesn't matter what's there. So the derivative of ln x was 1 over x, so the derivative of ln 4x plus 5 is 1 over 4x plus 5 times the derivative of the inside. Remember, that's what's new there. We actually do the derivative of x here and multiply by 1, but we don't really write that down. All right. And then minus 2, again, it's the ln of something. So it's 1 over that something times the derivative of the inside, which in this case is 3x plus 1. So the derivative of 3x plus 1 is just 3. So that's much easier to differentiate than trying to tackle it with the quotient rule up at the top. So I can tidy this up quite a bit. I'll leave the 1 over y there for now. So this is just 1 over x. Here I have 4x, which is being multiplied, so it's on the top. But it's also going to be divided by a 2, so that can reduce to a 2. So that 2 would be on the top. So this is plus 2 over 4x plus 5. Then minus, I see a 2 over 1 times a 3 over 1. That means a 6, and that's a 6 is on the top, over 3x plus 1 is on the bottom. And I could try and add these together, but this is where I've changed the question a little bit, and I'm not going to try and find a common denominator with these three things and go any further, because I'm going to substitute in x equals 1. So I'm actually finding the slope at this spot. So I'm not going to simplify there, but I can bring this 1 over y over and go y times 1 over x plus 2, 4x plus 5, minus 6, 3x plus 1. But now I'm going to sub in x equals 1. Sub x equals 1. Now the y part, I can go back and replace with the original question. So the y part is x. Actually, I'll sub in the 1 at the same time. So remember, it was x, so 1, times the square root of 4x plus 5, so 4 times 1 plus 5. All over 3x plus 1 squared, so 3 times 1 plus 1 squared. Just in case you're not seeing that step, remember that y, the original question from up top, from right here, is x over 4x plus 5 over 3x plus 1 squared. So I've replaced the y with that, but then substituted x equals 1 at the same time. The x equals 1 can get substituted here as well. So instead of 4x, it's 4 times 1 plus 5, and 3 times 1 plus 1 with the 6 on top. And now at least I'm dealing with numbers and not trying to find common denominators with some crazy x's in it. And the rest is just a little bit of exhaustion of doing the actual math here. So it's 1 times, underneath the root sign, you see that's a 4 plus a 5. So that's going to be root 9 on top, which I think you'll see is 3. Let's actually just replace it with a 3. I think we can see that in our head. So it's root 9 or just 3. And on the bottom, it's 3 times 1, which is 3, plus 1 is 4, squared is 16. Over here, this is just 1. I'm going to guess that I'm going to need a common denominator, so I'll just leave it as 1 over 1. On the bottom, it's 4 times 1, which is 4, plus 5 is 9. And over here, 3 times 1 plus 1 is 4. And now maybe you'll go to your calculator, maybe you'll go however. I'm just going to finish it off quickly. So I need a common denominator of 36 with these. So that'd be 36 over 36. 9 times 4 gets me 36, so 2 times 4 is 8. And then 4 times 9 is that, so 9 times 6 is 54. Common denominator, so I keep the denominator and add the numerators. 36 plus 8 minus 54 is negative 10. Now I can multiply. I can simplify first though. Divide the top and bottom by 3, so that would be a 1 and a 12. And here I can divide the top and bottom by 2, so this becomes negative 5 and 8. And that's going to make my final answer negative 5 over 8 times 12, which is 96. And that is the slope at this spot. So this can be an overwhelming question, but you notice that most of this is using answers or the laws of logarithms to make the question easier. That's the last blue line there. And then the calculus part is just the first green line where I'm taking the derivative of all these longs. Much easier. And then everything after the red here is substituting 1, and it's just brute forcing through the rest of the numbers. Okay. So when you look at it as a whole, it might be difficult to see on your screen, but you can see all the steps that we did to find the derivative and then the actual slope of the tangent at x equals 1. So this is where I'm going to, if we were live in your class, I would ask you to try this one up on the whiteboards. So you can ask the supply teacher to go off and allow you to do that. But for the sake of this video, you could pause here and try it. But I do have a full solution for this. So there's the full solution. Again, you'll see I did the same idea. I took the ln of both sides, and since I'm dividing, I can take the ln of the top minus the ln of the bottom. Gains me access to the exponents, and then differentiate. And this time I'm subbing in x equals 2, so I get down to negative 84. I promised you that I would show you that you could also answer these questions using your quotient rule from before. So here's this whiteboard question that you could do using the quotient rule. It's not bad, especially this one. The first one would have been a little bit more challenging using the quotient rule. But you can see that we end up with the same answer. You get m equals negative 84. But what we're practicing here is logarithmic differentiation. So I would rather you solve this using logarithmic differentiation. So use the laws of logarithms to simplify the question, then differentiate, as opposed to doing a question that we would have already done before. Okay? So I'm just proving that it gets the same answer with either method, which means logarithmic differentiation is something that works. Okay, so there's some textbook questions. Oh, there we go. That you can do some practice of this. This is definitely just a useful tool to be able to differentiate some pretty complicated ones using logarithmic differentiation. Good luck.